present When Water is Worth More Than Wood, Hydroclimatic Change and Its Consequences. Please join me in welcoming Bob Sanford.
Well, thank you very much for a kind introduction and also for the invitation to speak tonight. And I have to say that there are a lot of friends in the audience here tonight. I'm just thrilled by that. There's also a lot of knowledge and experience. And I know from this group there's an awful lot of people who care a great deal. I also have some friends here, Dale and Kathy, who I've known for most of my adult life, which the adult part was not that long. I also have, of course, Ron Casey, the former mayor of Canada. And Ron was the mayor, as I indicated. But the last time we were in a public forum like this, I said publicly that his town didn't charge enough for water. And he responded by telling me, personally inviting me, that I could pay more. I'm also thrilled tonight to have David Swan here, man, in my view, a great integrity man who has made not just ritual but actual sacrifices in service of this province and country. And I also want to point out, as was indicated in your presentation, Gordon, that it's really important to talk to me. And I want to introduce Lynn Martell, who's a journalist. So if you have views, I'm sure we'll talk to her. So I'd like to begin, if I may, by accepting my work. Centered in Tokyo, the United Nations University System has 18 different research institutions located in 14 countries around the world. And the mission of the United Nations University is to resolve pressing global problems related to survival, development, and welfare of concern to the United Nations and its member states. And each one of these institutions deals with a different challenge. And as it happens, the United Nations Institute for Water, Environment, and Health is located in Canada at McMaster University of Canada. And let's point it out in the introduction that our work really is to try to build a better bridge between science and public understanding that results in better policies. And to that end, what we try to do is to bring international examples to bear on Canadian water and climate-related issues. And our goal here is to put what others are learning elsewhere before the public and decision makers in Canada for their consideration. And I'm sure many of you have noticed that water and climate have become hot issues. So you don't need to be a rocket scientist to figure out that our weather is becoming erratic. Rainstorms, ice storms, and snowstorms are paralyzing our transportation and electricity distribution systems. Both high and low temperature records are being broken everywhere. Cold snaps are persisting. Snow is falling in places and in volumes seldom witnessed before. Flooding is occurring widely, and droughts are lasting for years. And what I have discovered in my protracted travels is that there's a growing sense across this country that there's something terribly wrong out there that goes far beyond our current global political, economic, and security goals. And whatever it is, it's coming at us fast, and it has something to do with water. But even with all this obvious evidence right before us, we still find ourselves tiptoeing around the issue of climate. And as one researcher indicated to me recently, and I thought this was a little cheeky, but I'll share it with you, climate is considered the new sex. You know, everybody knows about it. A lot of people are experiencing it, but nobody wants to talk about it. So, what can we say we actually know? What have we learned that is going to help us understand what's happening that we might be able to apply to this very important issue that you're here tonight to discuss? Well, one of the great breakthroughs in the earth sciences and the realization of the extent to which that which we consider to be a solid physical part of the world is in fact the creation of living things over time. Take, for example, the Earth's atmosphere. We're taught as children that the atmosphere of this planet is composed of 78% nitrogen, 21% oxygen, 1% argon, with a few traces also of carbon dioxide, neon, helium, methane, krypton, hydrogen, nitrous oxide, xenon, ozone, iodine, carbon monoxide, and ammonia. We also know that there's a lot of water vapor in the atmosphere at lower altitudes. From this description, one might surmise that the atmosphere is really nothing more than a transparent swirl of inert gases that somehow came into existence by way of the birth and evolution of the planet. But now we know that that is not so. What we're seeing when we look upward into the blue of the sky is not just air, but the suspended residue of every geological event and cumulative exhalation of every life form and ecological process that has ever taken place on or near the surface of this earth and its oceans since the beginning of time. What we know now, definitively, is our atmosphere is in part a byproduct of life. We've also learned that the atmosphere is extremely sensitive to changes in its own composition, particularly with respect to relative volumes of trace gases that have the capacity to hold heat. And I know that this is stating the obvious, but sometimes I don't feel in Alberta that that's necessary. To claim that the tiny percentage of carbon dioxide in the air can't affect climate is to deny the fundamental laws of atmospheric physics. It's like saying gravity doesn't exist. We know that carbon dioxide is fatal at 35 parts per million, less than a tenth of what the current concentration of carbon dioxide is in the atmosphere. Cyanide gas is fatal at 135 parts per million. So if there was the same amount of cyanide gas in the air as there is carbon dioxide, advanced life would cease to exist on the land of this planet. It's also often argued that humans couldn't possibly influence something as large as our global atmosphere. The Earth's atmosphere, however, is only 1/500th of the volume of our oceans, and look what we've done to them. Now, yes, of course, there are other factors that influence climate besides carbon dioxide, but when you put them all together, their influence doesn't begin to explain warming. We know, for example, that the output of the sun has not been a significant influence on global temperatures for the last 50 years. Very careful, repeated research has concluded that changes in the Earth's orbit will not appreciably affect atmospheric temperatures for probably another 30,000 years. And of course, warming will eventually decrease carbon dioxide concentrations by way of weathering, but that cycle takes 500,000 years to kick in. Human activities also, it should be noted, are presently pumping out carbon dioxide at a rate that's 50 to 100 times faster than volcanoes. So when you look at it that way, modern volcanoes emit only 1 to 2% of human emissions. And despite the localized cooling effects of La Nina events and other ocean current influences, average global temperatures continue to rise. This is the 357th consecutive month of temperatures above the 20th century average globally. So what this means is that if you're younger than 29 years old, which is to say that you were born before the end of March 1985, you live in a different climate regime than the rest of us. And the other thing we need to keep in mind is that water vapor in its own right is a powerful greenhouse gas. And the more water vapor there is in an energized atmosphere, the warmer it becomes. So you can see from this that the melting of the world's snow and ice becomes a climate feedback in its own right. Some of you will know that 70% of the world's fresh water is trapped in ice. Not anymore. There are a lot of other things going on at the nexus of ice, snow, and water. And as this nexus changes, what we're learning is that the cryosphere, that part of the world covered by snow and ice, actually plays a critical role in the function of the Earth's system. And in addition to their influence on sea level, ice and snow also operate as a global thermostat. Heat exchanges associated with phase changes between solid and liquid water help set the global thermostat that controls the temperature and the circulation of our planet's oceans and the behavior of our atmosphere. So weather and climate are regulated by that thermostat. What we're also seeing is that warmer temperatures are causing changes in the rate and the manner in which water moves through the global hydrologic cycle. And really, when you think about this from an atmospheric physics point of view, there's nothing surprising. One of the most fundamental laws of atmospheric physics decrees that for every degree Celsius of warming, the atmosphere will carry 7% more water vapor. And if you increase the temperature of the atmosphere by 2 degrees Celsius, the atmosphere can carry as much as 14% more water vapor. And if you raise the temperature of the atmosphere by 4 degrees Celsius, it'll carry more than 25% more water vapor. Now, this relationship, I should point out, is non-linear because the percentage increase is always added to a higher number. And that's why recently identified phenomena, such as atmospheric rivers, demand our full attention. These huge rivers of water vapor aloft carrying more and more water and are causing flooding of magnitudes that we have never witnessed before. And we recently discovered, and this is very interesting, that atmospheric rivers derive their energy from temperature differences between the poles and the tropics, and their intensity also derives from the Clausius-Clapeyron relation in that the warmer the air, the more water vapor atmospheric rivers carry. Other critical weather phenomena are also tremendously influenced by differences in the temperature gradient between the poles and the tropics. And the loss of Arctic sea ice and the reduction of the extent and duration of snow cover in the northern hemisphere are reducing that temperature gradient between the pole and the tropics. And it's this difference in temperature between the polar region and the warmer air to the south that largely defines the behavior of the jet stream. And the less ice there is in the Arctic, the slower and wavier the jet stream becomes and the more erratically it behaves. And we've seen from the altered behavior of the jet stream that warmer atmospheric temperatures don't automatically translate into warmer weather. In a uniformly warmer and therefore more turbulent atmosphere, both warm and cold fronts end up in persistent places in the mid-latitudes in which they were not common in the past. And that's how you end up with erratic weather everywhere, and how you end up with a polar vortex parked over central and eastern Canada for the entire winter of 2013 and 2014. And that's why, in combination with our atmosphere's capacity to hold more water vapor, both rain and snowstorms are persisting longer and causing greater and greater damage. What we're also seeing is that changes in atmospheric patterns are pushing major subtropical storm tracks toward the poles, often causing flooding of magnitudes we're very poorly equipped to manage. And that storm intensity is increasing, and that it is so was really obvious, as I will show you in a moment, in Canada during the summer of 2014. But most devastatingly clear this past year on the Canadian prairies, which experienced catastrophic flooding for the second time in 4 years. Presently, and this is important to know, the most obvious effect of changing hydroclimatic regimes on the prairies is this poleward advance of subtropical storm tracks. But there's another problem, the specter of deep and persistent drought. What appears to be happening now is that this warming is producing a flooding circumstance, but we don't know if there are other invisible thresholds that will be crossed as mean temperatures continue to rise. Temperatures on the prairies are expected to rise between 5 degrees and 8 degrees Celsius. We're already seeing droughts ended by floods in the same basin in the same year. We don't know at what threshold of temperature increase that the hydrologic coin will land on its dry side. All we know is that sooner or later it will happen. Now, it could be said then, if you look at that water and weather are essentially the same thing. And we've known that for some time. It was 20 years ago that Dr. John Pomeroy at the University of Saskatchewan first observed that fresh water is at once both a mediator and a transmitter of weather and climate change effects. And water, he said, shouldn't just be viewed as a substance, but as a flow of mass, energy, and biochemical constituents through and between ecosystems and between the land surface and the atmosphere. And what he suggested then was the presence or absence of liquid water, water vapor, snow and ice. That's what transmits climate change impacts across the country and across ecological and political boundaries. And that appears to be what's happening now. At a recent high-level meeting at the World Bank in Washington, it was pointed out that there is some real urgency in doing a better job at helping leaders and the public understand how these hydroclimatic changes are affecting us. Now we know that hydrologic conditions on the planet have always been changing. And we know also that we've been fortunate, especially here, to have had a century or so of relative hydroclimatic stability. That era is over. The long-term hydrologic stability of the climate we experienced in the past will not return during the lifetime of anyone alive today. What we haven't understood until now is the extent to which the fundamental stability of our political structures and global economy are in part predicated on relative hydrologic predictability. And as a result of the loss of relative hydrologic stability, political stability and the stability of our global economy in a number of regions in the world are now at risk. A strong case was made by the World Bank that hydroclimatic destabilization is now a major threat to advancing development. Extreme weather events now, in fact, are seen to be reversing development in some regions. And I'm going to give you an example that's far away, then I'm going to come closer to home. An example of this is Pakistan. In 2010 and 2011, Pakistan was impacted by major floods caused by an atmospheric river, which caused heavy rainfall during the monsoon period. And what's interesting is land use changes had altered the natural drainage patterns and river flows, aggravating the flood risk. So 2,500 people died. 27 million people, almost the entire population of Canada, were displaced. Some 200,000 livestock drowned, and 7 million hectares of Pakistan's most fertile cropland went unseeded. And the economic losses were anticipated to be around $7.4 billion US. And the key thing here to note, and again, this is important to know who's talking about this, is that the country's development has been reversed, set back perhaps by decades. In a separate meeting with the Disaster Risk and Climate Change Unit of the World Bank, they now have one. And I know that I'm talking here about a bank, not an environmental law. It was clearly stated that we now have to start thinking the unthinkable. The unthinkable, of course, is that these kinds of events might reverse development here in North America, thereby reducing or threatening our prosperity. And the fact is that it's already happening in Canada, we just don't see it yet. Where it's happening is on the prairies, but as you'll see, there's no reason not to believe that a local version of this movie will very well be playing soon at a theater right across the country. After the prairie flood of 2011, our initiative worked very closely with the Center for Hydrology at the University of Saskatchewan to analyze the hydrologic circumstances on the prairies. And it was our view, as I mentioned, that Manitoba had crossed a visible threshold into a new regime, and in that regime there was an increasing likelihood of more frequent, longer duration, heavier flooding as a consequence of regional land use alteration, drainage channeling, stream flow changes, and the intensification of the larger hydrologic cycle. And it was our view that what was happening in the Lake Winnipeg Basin was emblematic of how the hydrology in the entire country is accelerating. And we were particularly concerned about Lake Winnipeg Basin, where agricultural runoff was creating algal blooms of up to 17,000 square kilometers of area in the summer. And we publicly stated that we feared that if these trends continued, that the crossing of this threshold could over time bankrupt provinces like Manitoba. And we didn't say that flippantly. That year, a quarter of Manitoba's productive farmland went unseeded. The total cost of flood damage in 2011, combined with disaster relief in Manitoba alone, was $1 billion, which contributed significantly to the province's 2012 deficit. But the damage didn't stop there. Lawsuits totaling more than $1 billion were later brought forward as a result of the 2011 flood alone. So I urge you now to consider how the effects of hydrologic change have impacted the economy and political stability of Manitoba since 2011. Even though politically toxic, an unpopular increase in the provincial sales tax was deemed necessary to catch up with and get ahead of the infrastructure damage caused by the 2011 flood. And as you might guess, coming from this province, that tax increase has remained a source of divisiveness and will undoubtedly be a factor in determining who forms the government after the next provincial election. But it was the year 2013 that really demonstrated that the prairies may in fact have crossed over an invisible threshold into the new hydroclimatic routine. But despite all of the attention it received, it was not the spring flooding in Alberta that provided the evidence of that transition. The flooding in Calgary was a 1 in 42-year event, well within the natural variability that we come to expect over the last century. We unfortunately just weren't ready for it. The really interesting climate story of 2013 is not Calgary, but the fact that despite a record late season snowpack, there was no spring flooding in Manitoba. And what most Manitobans have probably forgotten already was that why the flooding didn't occur. And it didn't happen because a series of other equally unlikely extremes came into play that slowed the melt of the record late season snowpack. So what you had is near cold conditions slowing the snow melt, while timely thaw and warm, deep soil temperatures accommodated twice the normal rate of soil absorption. And what the United States Weather Service wanted people to understand in reporting this was that because there was no flood in 2013, did not in any way mean that the hydroclimatic regimes in the Red River Basin had somehow returned magically to what had historically been perceived as normal. They wanted the public to know that we have entered a period in which more frequent extremes and hydrologic conditions now make it impossible to use the past as a guide to prediction in the future. Then comes this past year. Manitoba again misses a spring flood, and though it was close, so did Alberta. Then pow, the flooding comes not in association with the spring melt, but as a result of remarkably heavy rainfall and early summer storms. And by July 4th, more than 100 communities in Saskatchewan and downstream Manitoba declared states of emergency. And in southwestern Manitoba, 50% of the land was covered by water, much of it in the form of floodwaters coming from Saskatchewan. And the flooding was so serious that farmers had to ignore the state of their crops and give full attention to saving themselves, their homes, and their livestock. 1 million acres of productive prairie farmland went unseeded. Some farmers have not been able to plant for 3 years. And I have to tell you, there's something new happening here, and that is the toll on people. I visited community halls that would turn into emergency centers, and farm families would stumble in, too exhausted, too distraught, even hold a pen in their hands to fill out forms that would have brought them financial relief. And while it's still too early to calculate the full cost of flood damage in 2014, that bill is over $1 billion again. And evidently, what were once loosely considered as 1 in 300-year events on the prairies have begun to appear every 3 years. And the prairies are not the only place experiencing this. On July 24th, 25 millimeters of rain, as much as normally falls in a month, fell in Kamloops, British Columbia. Now, what's really interesting about that is that at the time of the storm, the entire region was in drought and the area around Kelowna was on fire. And on August 4th, 200 millimeters of rain, more rainfall than normally falls in 2 months, fell in Burlington, Ontario, in the length of time it normally takes to get through the morning rush hour. In the Toronto and region, there have been 3 1 in 100 and 6 1 in 50-year storms in the last 25 years. Nor were our neighbors to the south spared. As August progressed, flooding of a similar magnitude was experienced in Detroit, Cleveland, and Long Island. And Winnipeg was also flooded in late August. And a week later, Steinbach, the nearby Niverville in southern Manitoba, got hit with 120 millimeters of rain, nearly 5 inches of rain in an overnight storm that overwhelmed flood mitigation systems put in place after the last flooding. So, there's a lot of troubled water out there, and it's trying to tell us something. What do you think it is that they're trying to say? Well, what water is trying to tell us is the hydrologic game is changing in fundamental ways, and careful examination of how our hydrology is changing suggests that there are ways to reframe our situation so that we can adapt more quickly and more effectively. And I wish to report to you that it's being put forward in many enlightened scientific and policy circles, not just abroad, but here in Canada, that our impacts are of such a scale that we have, in essence, entered a new geologic era in which human activities rival the processes of nature itself. And they're calling this new geological era the Anthropocene. And the foundation of this idea rests on new understanding of how the Earth system actually works. 4 components in tandem appear to regulate the stability that makes conditions for life on this planet possible. And these include the atmosphere, of course, the air we breathe, the hydrosphere, the water we drink, the cryosphere, which provides the refrigerating influence of the Earth's snow, glaciers, and ice sheets, and the biosphere, the living elements of our planet. And through our activities, we've changed the composition of our atmosphere, and our land use changes and water demands have altered the hydrosphere. Rising sea surface temperatures are shrinking the cryosphere, and our agriculture and growing global presence are reducing biodiversity. So things have started to change. And what the concept of the Anthropocene recognizes that humanity has in itself become a major force in changing the nature of the Earth's surface. It's really hard to deny that. We've become a force in our own right in terms of weathering and erosion. We've also altered global carbon, nitrogen, phosphorus, and water cycles. We're causing changes in the chemistry, salinity, and temperature of our oceans and the composition of our atmosphere. So, we see what we're doing. The idea of the Anthropocene is that we should stop ignoring what we've done and start recognizing what we have to do. We have no choice now, for example, to work with a changing climate, not against it. We have to prepare for more powerful storms and more frequent flooding, because that's likely what we're going to get. So, what are the implications of all of this? Well, the loss of hydrologic, hydroclimatic stability on the Great Plains, for example, makes the established bell curve of climate risk meaningless, the bell curve that we've used until now. So in a more or less stable hydroclimatic regime, what you're doing is you're playing poker with a deck you know, and you can bet on risk accordingly. The loss of relative stability is playing poker with a deck in which new cards you've never seen before keep appearing more and more often, ultimately disrupting your hand to such an extent the game no longer has coherence. So the Anthropocene on the prairies, we suspect, is going to be very turbulent. But I find it really interesting because, perhaps not surprisingly, given the nature of our contemporary social media, we actually have this iconic image of the geologic period we're entering is going to be right, you know. And it's still a frightening image, certainly, but you know, it has an overall tone of optimism. So I want to tell you this story about this, because it's really interesting. On Saturday, July 5th, 2014, a young Saskatchewan couple chose to have their wedding photograph taken on a country road just outside of Regina. And a tornado formed in the distance behind them, and later blew down and flooded their reception tent, scattering the wedding guests. Now, the bride characterize this brave new world in which we live on Facebook, and you're just going to love this. Here's what it said. We captured once in a lifetime moment and feel so lucky to have it as a memory of how, in such chaos, we always have each other. It's going to be smoking hot in the Anthropocene. So, what does it mean to have entered an era in which we can no longer count on self-willed natural landscapes to absorb human impacts on Earth system function? What this means is that we have to take sustainable development seriously. We have to take sustainable development to a new level. Our deteriorating global environmental circumstances tell us that what we thought was sustainable isn't. We have deluded ourselves in Canada into believing that because we are a prosperous nation, our development is sustainable. And what the loss of hydrologic stability tells us, that true sustainability may be beyond our grasp if we don't do the right thing now. If we want a sustainable world, we have to catch up with and then reverse the damage we have done to the Earth system and its functions before population growth, further ecological decline, and climate disruption destabilize our already fragile global economic system, making implementation of true and meaningful sustainable development goals unaffordable. One of the most immediate and cost-effective ways to do this is to invest in thoughtful, forward-thinking management of our total water and water-related natural resources. And it's already been well established that the careful management of water's role in ecosystem function is a form of insurance against threats to the stability of the life systems upon which all of us ultimately depend for our livelihood and our prosperity. But to be of any use to us, we have to buy the insurance. We have to buy the insurance, and we do that by protecting upland watersheds. We have known for thousands of years that deforestation of the upper regions of watersheds can result in increases in mean temperature, diminishment of precipitation, and over time, and in themselves create climate change. Previous civilizations have learned this at enormous cost. And we've observed for generations, for example, that forests actually create rain. We now know how. Forests create their own rain by seeding clouds with bacteria that float up from the trees and soils and serve as nucleators for the formation of ice crystals that initiate the first step in the formation of rain and clouds. So typically, water vapors high in the atmosphere bind together to form such crystals only at temperatures below freezing. And these bacteria from the trees and the soil allow such crystallization to occur at much warmer temperatures by virtue of the fact that they can contain a kind of scaffolding in which the structure of their proteins allows water vapor in the air to coalesce and bind together around the bacteria itself to form raindrops. This doesn't happen when you cut your forest down. What happens is the rainfall declines. And when human activities reduce ecological function through land use impacts, water's actual and potential role in the self-organizing process of living systems is also diminished. And if this role is reduced below certain thresholds, effective systems can no longer act as buffers to disturbance. We know that supplying water to nature is crucial in preventing ecosystems from passing from one state to the other, such as forests turning into grasslands, prairies, and deserts. We also know from research conducted again by John Pomeroy and others nearby here in the Kananaskis that intact forests will protect surface water resources through mean annual temperature increases of up to 4 degrees Celsius. Protect intact ecosystems and you can moderate and even slow climate impacts. And this fact in itself suggests that it's no longer enough that development be sustainable. In our case, it has to be regenerative. This new level of sustainable development must start with full realization of the value what we already have. And I was really taken by Gord's, I saw Gord's PowerPoint in advance, and I was really taken by his images of grizzly bear and the dam. And I'm going, well, that's really good. But I noticed that we were looking at completely different things, you know, and certainly we want to sustain the ecological integrity the grizzly represents, as Gord pointed out. But I was looking at this den and I was seeing something else, you know, and while the great bear truly and utterly matters, we should not forget that what is under the bear and all around it in its living den really matter also. And dirt is one of these natural features, like the atmosphere, that if you aren't a farmer or a gardener, you might think principally about it in terms of physical terms. But like the Earth's atmosphere, soil is in fact the creation of living things over time. And good soils are porous and as microscopically alive as a coral reef, and just as crucially central to the vitality of the larger systems they bring into existence and support. The bacteria, fungi, protozoa, nematodes, and microarthropods, and all the creatures that rely upon them, such as earthworms, beetles, and voles, and everything upward from that, form what is known as the soil food web. And all of you in this room will know that this is the foundation of life on the terrestrial Earth. What we're seeing globally is that we're destroying our soils. Worldwide, we're trying to make up for diminished natural soil health by replacing with artificial fertilizers, which wash away with depleted soils and contaminate water and floods that could be prevented by restoring these soils. And the compacting of soils has also become a global problem in that it does not permit soils to absorb and retain water over the long term, as Gord alluded to. And one study demonstrated that nearly half of current global sea level rise can be attributed to water that comes from runoff from compacted agricultural lands that could be prevented by healthy soils. So what we see is that different ecosystems generate different soils which capture, purify, and release water at different rates. And upland forests, for example, modulate the hydrologic cycle by absorbing heavy rains, enhancing the seepage of water into the ground, which is held firmly in place by tree roots, and which allows, as Gord indicated, to reduce surface runoff. Now, this is very interesting, though, because in the best uncompacted soil, microbial and fungal aggregates become tiny subsurface dams. You know, we're talking about building these big dams, but you can build trillions of them in the soil, and each captures a precious reservoir of water. Organisms move around on the thin film of water that forms between and within these soil aggregates. So healthy soil, rich in microorganisms in their aggregates, holds water like a sponge, releasing it slowly to plants as well as to aquifers, streams, and rivers. And in combination, these effects even out the release and availability of water throughout the year. So what we're seeing now is healthy soil is probably the best protection for crops during drought, as well as the best protection from floods. And this is quite interesting. A 2012 test demonstrated that deep, healthy soils can absorb up to 8 inches, more than 20 centimeters of rain an hour without generating floods. So these also, soil-rich microorganisms, will attack and eliminate pollutants from water, eventually draining it into an aquifer or stream in pure form. Healthy soils remain, really, humanity's first and foremost water purification system. And I was really glad that Gord alluded to this, because the rebuilding of soils is now seen as a means of enhancing natural processes of water purification, is now seen globally as really smart urban planning. And that's why 200 cities in 29 countries have forgone building new water treatment plants and instead invested in watershed restoration that that also cleans up pollution downstream while at the same time affecting flood protection. Now, but I want to point something else out. Soil does something besides grow forests, supply food, and absorb and purify water. It stores carbon. And it's now estimated that we've already lost as much as 80 billion tons of carbon from our soils through inappropriate agricultural practices and short-sighted land use. keeping and getting carbon into the soil may be one of humanity's most important priorities. I want to point out that all current Intergovernmental Panel on Climate Change warming projections are based principally on the effect of increased carbon dioxide and other greenhouse gases in the atmosphere. They don't take into account ecological responses to that warming. And it's now been demonstrated that in the top 1 foot, or about 25 centimeters of the Earth's soils, there's approximately 4 times more carbon locked up in an organic matter than is presently in the atmosphere. Now, here's the problem. And here's the problem with clear cutting, too. When you warm these soils, the carbon in the soil burns off as carbon dioxide. And it's been projected that a 2 degree Celsius mean global temperature increase could burn off 25% of the carbon presently stored in the top layers of the soil, which is an amount equivalent to that which is presently in the atmosphere. And in other words, if globally soils warm by 2 degrees Celsius because of changes in the heat-absorbing capacity of the atmosphere, then we could expect the carbon dioxide concentration to double from its present 400 parts per million to 800 parts per million. It is with good reason, then, that soil and water are increasingly seen around the world as strategic national assets. We have we have to manage soils with the same attention that we manage forests. And there are huge rewards for doing so. It has been recently demonstrated, for example, that even in arid regions, soil carbon can be increased by 60% and water holding capacity of the soils by 30%, while at the same time increasing production of food through effective soil management. And you have to see that as a promising finding. Through restoration, 3 billion tons of carbon could be sequestered out of the atmosphere into your soils, reducing atmospheric carbon dioxide concentration by 3 parts per million. So in other words, through astute soil conservation, we could conceivably slow and possibly even reverse warming. Soil restoration could, in the end, do what expensive geoengineering proposals promise to do, and do it for free. So, back to the ghost. Now, this logic proposal offers an opportunity to reevaluate what our upland forests do for us. And I want to point out to you that I work widely, not just in this country, but I can tell you with conviction that sustainable development does not mean putting a few more parameters forward for mitigation in advance of the expected approval of a development. It means that all parameters associated with any development, whether it's a bridge or a road, a subdivision, or a cut block, meets a standard that will ensure that development will not over time compromise the character of place, diminish biodiversity, or reduce the opportunity of others in the future to live at least as well as we did in our time. And you subscribe to this level of diligence in the planning of development so that each additional element adds not just to the immediate value of what we have, but to the likelihood and stability of human presence in a given place over time. And if you aren't strict about the conditions of sustainable development, then places generally decline until first they are impoverished, and then they are barely inhabited. And if you've been to places long inhabited by people, such as the cradles of civilization in the Middle East, or China, or India, you know what this decline looks like. And what we learn from these places is that very wealthy and highly sophisticated civilizations can come into existence, but if their development is not sustainable, they can diminish local environments enough to bring about decline. So if you don't impose strict conditions on development, places can literally become poorer and poorer to the point of de-development. We also know that you don't have to burn fossil fuels to bring about civilization collapsing climate effects. All you have to do is cut down enough trees. The changing climate will do the rest. Now, from examples all over the world, we also know that it's seldom lack of foresight that undermines national efforts to achieve meaningful sustainable development. Corporate self-interest that drives weak or short-sighted policy can slow or reverse gains in sustainability, biodiversity conservation, and social justice, and in so doing, undermine efforts to improve governance, political transparency, ethical standards, and standards of business practice. Traditional debates of the kind we're having over logging and the ghost have historically revolved around threats of wildlife loss, the loss of natural scenery and quality of life of residents. But in the case of the ghost, we're talking about much, much more. So in conclusion, what in the context of the new geological era in which we've entered are the real sustainable development trade-offs here? Well, certainly there are considerable trade-offs in ecosystem services. Giving up the ghost means sacrificing the capacity of upland forests to slow and moderate climate change effects. By clear-cutting the forests and compacting the soils, we're taking away free natural water storage and purification services for southern Alberta communities. We are compromising critical wetland ecosystem function. The trade-off also includes diminishing flood and drought mitigation, resulting in compromised societal resilience to disasters. This means we're permitting the developer to pass on to the public all financial and personal costs associated with potential future downstream flooding. Those flooding elements associated with these activities. And as Gord said, logging as proposed, is in the most biologically productive areas. That means where the best soils are. Now, soil health and attendant critical carbon storage are also being compromised, making it harder to deal with the fact that temperatures are already on the rise throughout the prairies and are expected to continue rising at a rate higher than of any other region in Canada except the Arctic. These are not the only trade-offs. There are trade-offs also in the way we live and in the manner in which we allow ourselves to be better. These very real democratic trade-offs are related directly to the risk a society takes when it unthinkingly continues to accept long-standing but dangerously outmoded political and economic status quo. If we give up the ghost, what we're essentially risking is water and climate security in that basin. And what are we being offered in exchange? Well, certainly some jobs in Cochrane, a few sticks of lumber, and a few bags of landscaping mulch. Is this sustainable development? You decide. I welcome you to the end.